Hello and welcome students to the sixth lecture of this course, which is called chemistry, and the course code for this particular subject is CH101 for the odd semester and CH201 for the even semester. And this is G. Chakraborty from the Department of Chemistry, and we are studying from the last lecture the topic which is called periodic properties. Okay. Now, as you can see that this is the sixth lecture. That means we have already come across 5 lectures, and the first 4 lectures were regarding the topic atomic structure that we will study in detail. So I guess atomic structure has given you some idea regarding the different type of elements that can happen and how these elements occur, what is present inside the atoms and all. Right. Now, as you know that we belong to the module 1 right now. We are doing the topic which are present in module 1, and the first topic was none other than that atomic structure, and the second chapter inside this module 1 is the periodic properties that we people are studying, right? And this module 1 is nothing but inorganic chemistry. Okay, now this is our knowledge regarding the thing that we have already claimed, right? Now in this part 2, what we will see that we will discuss, but before that let us discuss what was present in the part 1 of this particular lecture, which is named periodic properties, right? Now in the part 1 there is lecture number 5. In the last lecture we people have seen that how the periodic table was invented. We have clearly seen that the first initial idea was given by Johann de Werner, and that particular person has done a wonderful job by trying to arrange the then known elements in some order of increasing atomic masses, and he has found some similarity. Okay, now this similarity was of groups of 3, right? 3 elements of the group used to have same type of properties, and he called these 3 elements in the group as triad, right? He named them triad. Okay, since 3 elements were present, and moreover he at that time, whenever he was doing the experiment, that time 20 elements were known, and a beautiful work regarding those 20 elements were done by Johann de Werner. Okay, now when de Werner established his theory few years later on, around 20-30 years later maybe, another scientist was named John Alexander Newlands, right? He was also a very good scientist, and he was very fond of music, I guess. So what he found out that whenever we arrange the elements in order of increasing atomic masses, I'm saying atomic masses, but again and again I'm trying to say that at that time the word mass was not known because gravity was not invented. At that time people were concerned about weight, so atomic mass was atomic weight at that condition. Okay, at that time. Now what people can see that when John Alexander Newlands have done his experiment, he found out that whenever we arrange the then known elements in order of increasing atomic weights, what we get an order, right? Now this particular order is such that the 7 elements can be present in a single period. That time period what was not known, but he found out that the 8th element resembles the first. So accordingly what he had done, he had arranged the 7 elements in a group, and the 8th element was given position just below the first element. Okay, that means the 8th and first are in the same group, right? Again I'm saying the group term was not introduced at that time. Okay, it was introduced later on by Mendeleev, right? So whatever Alexander has done, he has said that this is similar to the notes of music, do re mi fa sol la ni, that means sa re ga ma pa dha ni, right? Now after his invention, he didn't get that much of importance, because just after his invention, 3-4 years later on, a big invention was done by Dmitry Ivanovich Mendeleev. Okay, now who was that Mendeleev? You people know very well, so I'm not discussing about that, who was Mendeleev. But the thing is, what he had done is of extreme importance in the history of this periodic table and the history of chemistry. Why? Because Mendeleev created the first periodic table in the history of the world. Okay, why I'm saying that? Because actually Mendeleev collected the elements, arranged them in some order, okay, and then he tried to form the periodic law, which said that the properties of elements are periodic function of their atomic weights, right? So if we arrange them in order to their weights, then we'll get some order. If we arrange them in increasing order of their weights, then we'll get an order in accordance to which many of them will show similar properties. Now Mendeleev said that okay, fine. If they are showing similar properties, then let's do something. What is that something? Let's just keep them in a group, right? So that such that a group of persons does the same work, a group of persons work together. So let us form a group, right? And he said that the vertical columns will be group and the horizontal rows which were present will be periods. So accordingly, he also named the groups as 1, 2, 3 or 1A, 2A, 3A like this. And he also has done a wonderful job because he left scope for the future elements also. That is, the noble gases can be inserted without any problem, right? So this type of scope were given by Mendeleev, right? So Mendeleev's periodic table was of extreme importance, and the concept of periodic law, concept of groups and periods for the first time came from his periodic table only, right? Now after that, the main discovery of the periodic table or rather I should say the modern periodic table, was discovered by Henry Moseley, right? Now Moseley also has done a wonderful job. What he has done? He has done X-ray diffraction experiment because X-ray was available at his time, right? So he has done the X-ray diffraction experiment and cleared that the whatever people are doing with mass, right, or weight, the atomic number is much more convenient than that. So if we use atomic number to arrange this particular elements, that means if the elements are arranged in order of increasing atomic numbers, then what happens? Their properties will be as such that they'll be easily arranged in the periodic table. Why? Because the main problem of isotopes will be over, and different other elements will also be over, right? Okay. So one thing I forgot to tell about Mendeleev, that Mendeleev also corrected the atomic masses of certain elements, right? Now after Moseley's periodic table being invented, main discoveries have come up, and the groups and periods were redefined, but the definitions are almost the same, right? And this new periodic table, whatever it looks or however it looks, we will have discussed in the last lecture. Okay. Now let us see what is present in this particular lecture. So in this lecture, it is nothing but the periodic table properties part 2. Here we people are having this as the lecture highlights. Okay. The first thing that we people will be having, basically we are evaluating the periodic trends here. First one will see the atomic structure, second one that we'll see is ionization enthalpy, third one that we are seeing is electron affinity, and the fourth one that we are seeing is electronegativity. Okay, right? So these things we will be seeing in this particular lecture. Now we need to know first that what is atomic radius and how it works, right? Now it is quite easy to remember that atomic radius is the radius of an atom. Whenever you will say atomic radius, I will say the radius of an atom. But it is not as simple as that, because there are multiple definitions, and how it varies also, that is also very important for us, how it varies across a group and along a period, right? Okay, so let us focus on this particular thing. The atomic radius is one half of the distance between the nuclei of two atoms. So if we take two atoms, the half of the distance between the nucleus of these two will be the atomic radius, just like radius is the half of a diameter of a circle, right? However, this idea is complicated by the fact that all atoms are not normally bound to each other in the same way. Yeah. See, I told you that it is not that easy as it seems, right? It is quite difficult. So, as the atoms are not bounded in the similar manner, so this distance calculation, the radius is not that much easy. Okay, now how it works, let us see. Some are bound by covalent bonds, some are attracted by, as in ionic crystals, and others are in metallic crystals. So different type of elements are there, different type of compounds are there, so different type of bonds are also there, and different techniques are also there to calculate the atomic radius. Nevertheless, it is possible for a vast majority of elements to form covalent molecules in which two like atoms are held together by a single covalent bond. The covalent radii of these molecules are often referred to as atomic radii. This distance is measured in picometers. Atomic radius patterns are observed through the periodic table. Okay. So what it is being said that if we are dealing with covalent molecules, or we can say rather the homonuclear molecules, then the thing becomes quite easier, right? Cl2, H2, Br2. In that case, what will happen? We can calculate the covalent radius. Accordingly, the covalent radius is said to be the atomic radius in that particular case. Okay. So this radius will be measured in picometers. That is also stated here, right? Now these are the periodic trends. Let us use some different colors. Say blue. The atomic structure gradually increases from left to right across the period of elements. This is because within a period or family of elements, all electrons are added to the same shell. However, at the same time, protons are being added to the nucleus, making it more positively charged. The effect of increasing proton is greater than that of the increasing electron number. Therefore, there is a greater nuclear attraction. Just try to understand what happens whenever you are going across a period. It means you are moving from left to right. Say we are doing it for third period. Okay, the third period means what type of this or for, let us say fourth period. Okay, now for the fourth period, what type of things are present? By things I mean to say what type of orbitals are present or what type of subshells are present. 4s, 4p, 4d and 4f, right? Four different type of subshells. Now what is happening whenever electrons are moving one by one, one by one, one by one? What is happening? The electrons are added to the same shell. Same shell means C. The shell is 4, right? For the shell, principal quantum number n is 4. So whenever you are adding either to 4s or 4p or 4d or 4f, what is happening? The electrons are going to the same shell but in different subshell. Now as it is added to the same shell, so shell number is not increased or shell size is not increased, but what increases is the attraction of the nucleus. Why? Because gradually electrons are getting protons are getting attached to the nucleus, due to which the nuclear charge increases. Now you may say that one electron is added, one proton is added. What the big deal? Okay, nothing should vary. Now one electron is added, one proton is added. So what is the problem? See, there is no problem, but the thing is the combined effect of the protons being added is much more than that of the electrons, because it is dispersed effect. Electrons are not added at the same time. Electrons are added in different places. They are moving in a single way, right? But the protons are added in the same nucleus. So it is quite easy that suppose you are a team, then your work will be good. If you are not a team, your single persons will work, then the work will not be that good. Okay, so it is just like that, nothing else. Okay, so combined effect of the protons is much more compared to that of the electrons. This means that the nucleus attracts the electrons more strongly, pulling the atom shell closer to the nucleus. Valence electrons are held closer to the nucleus of the atom. As a result, radius decreases. So proton is having more power, nucleus is getting more positively charged, attraction between nucleus and electrons increasing. 1, 2, 3, it is increasing day by day, right? Not day by day, it is increasing with the addition of electrons rather. And this electron will result in decrease of the distance between the valence shell and that of the nucleus. Okay, so gradually what will happen? The atomic radius will decrease. Okay, this was the discussion along a period. Now let us use some other pen, say brown. Okay, and discuss about the group. Now down a group, atomic radius increases. The valence electrons occupy higher levels due to the increasing quantum number. Valence electrons further away from the nuclear increases. Electron shielding prevents outer electrons to being attracted from the nucleus, to the nucleus. They are loosely held, resulting in large atomic radius. So what is happening? It is quite easy to remember that one shell is added whenever one electron is added, whenever we are going from top to bottom. So if the shell is added, then what will happen? Automatically attraction will be less and the size of radius will be more. Okay, so that's how it is. Let us go to the next slide. Now, as you can see, this particular image is something I love. Okay, now why I'm saying this? I think you will love it too, because here clearly you can see the size of the atom by simply looking at its position, right? You can see that the smallest element of the periodic table is helium, okay, followed by neon, okay. Fluorine is also very small, right? Now if noble gases are just not considered, then fluorine will be the smallest, right? Now as you can see any of the periods from the left, the this particular thing, the alkali metal is having the greatest height, and as you are moving from left to right, then what is happening? The atomic size decreases. As a result, what will happen? The atomic radius will also decrease, right? Now it is written atomic sizes are related to the largest element cesium. Yes, cesium, we can see this is cesium and it is the largest in the periodic table. Deemed elements have no data. Elements 87, 88 and 104 to 118 have no data and were omitted. Okay. Now as you can see, another important thing is that we'll discuss about it. But before that, I want to discuss about lanthanides and actinides. You can see, moreover, their size is same. In the middle, some of the elements are small, right? Now you may say, why this abrupt thing is there? It should be like this, from greater to smaller. Why the first one and the last one are almost of similar size? Why? What is the reason behind it? You may say. Thing is that there is a phenomena which is called lanthanide contraction and actinide contraction. I think you people have studied in class 11. Okay, so due to not 11, in 12. In lanthanide and actinide contraction, what happens? There is a shielding effect that goes on, due to which the attraction becomes less. As a result, more or less the structure remains same, but this actually is abnormality for some elements like neodymium and promethium. So their sizes are comparatively small in between. Okay, right? Now as you can see, if we go to the top side, you can see from going from top to bottom in each and every group, the atomic size is increasing from the top one having the largest to the bottom one having the from the top one having the smallest to the bottom one having the largest. Why? We have been discussing it in the last page. Okay, last slide. Now as you can see that from left to right also, first one is big, then small, finally extremely small atoms are there, we can see. Okay, so this is all about the atomic sizes. Now I think this idea, this picture has given a great idea to you people that what the atomic radius is across a group and along a period, right? Now with this particular data with us, let us go to the next slide. So we are having ionization enthalpy as our next topic. Okay, let us see what it says. Now a quantitative measurement of the tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from a gaseous atom in the ground state. In other words, okay, fine, fast ionization enthalpy we will discuss about it later on, but let us discuss what is ionization enthalpy. Let us come to the fact what is ionization. Ionization means process of formation of ions. Now we are having an element, it will become an ion, right? Process is called ionization. Now this process can be of two types. One is formation of cation, another is formation of anion. What I am talking about? I am not talking about ionization enthalpy. I am talking about ionization only, right? Okay, now whenever it comes ionization enthalpy is the energy change that happens whenever an ion is formed. Okay, now this is a theoretical definition, right? Now what the experimental definition is? Experimental thing is that whenever an ion is formed, that means whenever a cation is formed rather, then what will happen? Some energy will be required. Why required? Because see, an element is electrically neutral, an atom is electrically neutral. Now you want to remove one electron from that particular atom, so you require some force, na? See, you are a healthy human being. Suppose somebody wants to take your kidney, somebody wants to grab your kidney, cut it off. So what will happen? You will give it as it is, or you will just say that no, it is not possible. You will give some resistance to him. I guess yes. Now if that person wants to take it from you, then he or she has to apply force, right? Now that force is nothing but energy. So here what is saying, if you want to take, let us forget about kidney and yourself, if you want to take an electron from an atom, then what happens? Energy will be required. That's why it is written that the energy required to remove an electron, okay, from an isolated gaseous atom. Now you may say, why gaseous atom? Because gases have less attractive forces between the atoms, right? Solids have maximum, liquids have intermediate, gases have almost none. That's why gases in the ground state. Okay. In other words, first ionization enthalpy will be denoted by delta IH standard, right? Now delta IH is nothing. I stands for ionization, H stands for enthalpy. Okay. Now here what we can see X is becoming X plus, right? It would have been better if we have written it as M, right? Because X denotes noble gases. So let us make it M. Yes, not looking that way, but it is M. Okay, let us imagine why I am writing M, because M means metal, right? So when M will become M plus, that means one electron is ejected. So this energy which will be released, right, that particular energy will be in terms of kilojoules molecules. Now second ionization enthalpy will be defined as in a similar way. It is the amount of energy required whenever electron is needed to be removed from the cation. See, already it has become a cation. You have made it here. If one more electron is removed, then it will become 2 plus, right? Now here what is happening? Somebody has taken your one kidney and he is now opting for your another kidney. So what will happen? You will just fight for your life. Okay. So that's why more energy will be required. Okay. Energy is always required to remove electrons from atom, and hence ionization enthalpies are always positive. Second ionization enthalpy will be higher than that of the first. See, I told you that if somebody wants a second kidney, then what will happen? Okay. Now it is more difficult to remove an electron from a positive charged ion than a neutral atom. In the same way, the third ionization energy will be higher than the second, and so on. Term ionization enthalpy is, if not qualified, is taken as first ionization enthalpy. Basically, whenever we say ionization enthalpy, we mean the first ionization enthalpy, right? Now this is the periodic trend of ionization enthalpy as we people are seeing in this particular screen. You can see that it increases from left to right, and it increases from bottom to top. Okay, and it increases diagonally also. See, now the simple answer can be, whenever you will say why, I will give you the very simple answer, most simplest answer of my life, I guess. In the left side, the atom is big. We have seen in the atomic structure data. If the atom is big, that means what? More and more energy is required. Less and less energy is required to remove the electron, because electron and nucleus are far apart. But whenever the atom is small at the right side, right end, then what will happen? Electrons and nucleus are close. Now somebody cannot take your kidney out whenever your parents are nearby, right? But they can take it out whenever you are far from your parents. So let us imagine nucleus is the parent and electrons are babies, right? So if the electron is close to the nucleus, or the atom is small in the other case, then it is difficult to remove the electron. More energy will be required. That's why at the right side it is extremely large, and the left side it is less. Similarly, at the lower part of the periodic table, that means whenever we move from top to bottom, size increases, hence IE decreases. Okay, as simple as that. Let us go to the next slide. So another important topic we are having here, that is electron gain enthalpy. Now what is happening here? When an electron is added to neutral gaseous atom, it gets converted to a negative ion. Enthalpy change is called electron gain enthalpy. This would have been delta, right? Electron gain, it is a measure of the ease with which electrons. Yeah. So basically, the tendency of getting an electron, the tendency of getting an electron is called electron affinity, right? And in terms of energy, we can say it is electron gain enthalpy. Same thing. Okay, electron affinity and electron gain enthalpy are same thing. So electron gain enthalpy, what is defined as, whenever an electron is added to a gaseous negative atom, then what happens? Some amount of energy will be released, right? Generally it happens whenever the electron is added, energy is released. Why? Because the atom becomes stable. Let us imagine we are having Cl. You add one electron, Cl becomes Cl minus. Getting the configuration of argon, it becomes stable. That is what the example has been provided here. Now, if it becomes stable, then what will happen? Energy will be released. Now the question arises, this was the first electron gain enthalpy. What about the second? Now after it is stabilized, If one more electron is to be added, then definitely it will not want to, then energy will be required instead of release. Okay, now you may say that what about oxygen? Oxygen gets two electrons to get stable. There also I think some amount of energy will be required, because whenever you are adding one electron, it already becomes minus, right? Outer shell has more electrons. If you add one more electron, then what will happen? Negative repulsion will come up. Now you have to overcome that repulsion, you have to add the electron, right? That's why. So let us see what is written. Depending on the element, process of electron adding. Okay, fine. For example, group 17 elements, it is highly electron enthalpy, because due to attain noble gas configuration. On the other hand, noble gas have positive and okay, fine. Noble gas have positive electron enthalpies because they don't want to take any electron, right? Leading to very unstable configuration. Maybe noted that electron enthalpies have large negative values towards upper right of the periodic table. Why I am saying this? Let us see it out. Let us see this now instead. Here it comes. So as you can see, if we go from left to right, the tendency of becoming negative increases, and if you go from lower to upper also, tendency increases. Why? Because again the same thing, nucleus and electrons are close to each other. Right side means smaller size, top means smaller size. So what will happen? Nucleus and electron will be closer to each other, and more attraction towards the valence shell occur. That's why addition of electron becomes easier, right? So this particular thing increases, and on the other hand, if we do the reverse, then it decreases, right? As simple as that. Now our topic is electronegativity. Now this is directly connected with the term electron gain enthalpy. If an electron has the tendency to attract electrons, that means if it has higher electron gain enthalpy, then it is electronegative. See, it measures the amount of atom's tendency to attract the bonded pair of electrons towards itself. This property exists due to electronic configuration, right? So in order to follow the octet rule, this particular thing happens. Because elements on left side of periodic table has less than half full valence shell, energy required to gain electrons is significantly higher compared to the energy required to lose electrons, right? So whenever we are going for the elements that are present on the left side, instead of gaining electrons, suppose let us imagine for sodium. Now it has 3s1, right? Or better example would have been aluminium. Aluminium has 3p1. Now just try to imagine it has 3p1. So is it better to lose 3 electrons and get rid of 3, or it is better to add 5 electrons? So whatever you say, I say it doesn't matter, because aluminium will say that I'll better lose 3 electrons than getting 5 electrons, right? That's why it has lower tendency to get electrons. But if we go to the right side of the periodic table, the reverse will happen. So what we can see, considering this, let us see the trend, then it will be clearly explained. The trend is like this. Again, a beautiful picture. See, here it is a 3D picture, as you can see, and it clearly implies that which one is having more electronegativity and which one is having less electronegativity. This picture has amazed me. Believe me, this picture has amazed me. And this Pauling scale, okay? Electronegativity is written on 1, 2, 3, 4. It is nothing but Pauling scale. I am amazed by the picture, really. It is awesome. So here you can see clearly what the value is. Also you can see which one is greater, which one is smaller. Now here the table, the structure, the picture clearly implies that the maximum electronegativity of 4 is for that particular thing, fluorine, and I guess the least is for francium. Okay, so that's all about today's lesson, right? And this was the second lecture and for the periodic properties, and overall it is the 6th lecture. Now let us look forward for this third part of periodic properties and the 7th lecture of chemistry. So till then, let us hope for the best and try to remember these things that we people have discussed. Okay, these are very important for you. Stay safe and stay healthy. Okay, study a chemistry a little bit, you will be more healthy, right? So that's all for the day. Thank you so much. See you in the next lecture.